Good morning, students. As I promised in our past two lectures, that I will continue to speak on process synchronization. Yes. So we are about to go a bit in depth into process synchronization. Processes have to synchronize. They have to synchronize to make sure the information or the data we are receiving has integrity. Okay. So we'll be looking at the background and the critical section problem. Then we'll look at some of the solutions to this critical section problem, which is semaphores, mutex, and serializability. Serializability, you meet it again in advanced database, and it is very, very important for banking sectors or financial sectors. So concurrent access to shared data may result in data inconsistency. What that means is that having access to data at the same time while somebody is reading, somebody is writing, you might end up using the wrong data because you won't have access to the updated data. So maintaining data consistency requires mechanisms to ensure the orderly execution of cooperating processes. Now, bounded buffer. So an operation like if you write a statement process one and it says counter plus plus, then you have process two, counter minus minus. So it should be performed atomically. When we say perform atomically, it should be performed once. So atomic operation means an operation that completes in its entirety without interruption. So it either performs once or it doesn't perform at all. Okay. So let's say if process one, right, holds process one has the variable P1 and P1 is holding a value of 5. When we go for counter plus plus, it is plus 1, so it'll be 6. Now imagine at the same time we are applying counter plus 1, then we are applying also counter minus minus to P1. It means that whilst we are incrementing, there is a decrement also happening, and this will lead to the inconsistencies in the data. Now you have P1 and P2. So it's saying that these operations should perform once. It should perform or not perform at all. So the statement counter plus plus may be implemented in a machine language as this. Register 1 counter, and register 1 is equals to register 1 plus 1. So the counter will be the contents that are in register 1. And likewise for register 2, we put the counter in register 2 and we say register 2 is equals to register 2 minus 1. And the counter will end up being register 2. This is simple programming. When you deal with data structure, you should be able to understand this very simply. So assume counter is initially 5. One interleaving of statement is this. The register 1 is equals to counter, so register 1 is 5. Register 1 is equals to register 1 plus 1. 5 plus 1 is 6. Then you go to register 2 and counter, so register 2 is 5. And you go to register 2, register 2 minus 1, which is 5 minus 1, that'll give you 4. So you realize that the counter, you have 6 and 4. So the value of count may be either 4 or 6, where the correct result should be 5. What is a race condition? It's the situation whereby you have multiple processes accessing and manipulating data at the same time. And the final outcome of the shared data depends on the process that finishes last. In other words, the shared data becomes inconsistent. So, to be able to solve this race condition problem, we must make sure that processes synchronize. Yes. So, what is race condition again? Race condition is a situation whereby processes access data. Everybody's struggling to access data at the same time. And while it's accessing the data at the same time, some could be reading, some could be writing. And this leads to an inconsistency with the data. And in order to resolve this inconsistency problem, we must be able to ensure that our processes synchronize. Now, how will our processes synchronize? This is where the critical section comes in. So the critical section is the section of code in each process where access to shared resources or data occurs. And it is the part of a process where the shared resources, and what are some of the shared resources? Something like file, variable, or database is accessed or modified. And thus, it must be executed in a mutually exclusive manner to prevent race condition or inconsistent result. When we say mutually exclusive, what we are trying to imply is that one has to execute before the other. That's what we mean. Yes. So there's a critical section problem. If n number of processes compete to use the same shared data, each process has a code segment called a critical section. So every process has a critical section in which shared data is accessed. Yes. So we know what shared data is. We said that shared data is either file, a variable, or database. So every program, every process has a critical section, and in its critical section, you see the problem is that it ensures that one process is executing in its critical section. No other process is allowed to execute in this critical section. And I gave you the scenario of having a house where you have three master bedrooms, and each master bedroom, of course, has its own toilet. And if I am in my toilet, no other person, so we consider the rooms to be processes. So if I'm in my toilet, nobody else can visit their own toilet. That's just how it is, you know. So the critical section, because the problem with the critical section is that we have what we have there is that each process has its critical section, and we cannot allow each process to go into its critical section at the same time. It should be one process entering its critical section at a time. So to be able to ensure that only one process is exploring its critical section, we can use solutions like mutual exclusion. We call mutex. We apply mutex lock. So if process P is executing in its critical section, then no other process can be executed in their critical section. Yes, so we place mutex locks on it. So then we have the progress. So if no process is executing in its critical section, and there's this some processes that wish or intend to enter their own critical section, then those processes that are not executing in their remainder section can participate on a vote or a decision to select which one will enter the critical section next. And this selection cannot be postponed indefinitely. Then you have bounded waiting. Bounded waiting means there should be a limit. A limit must exist for the number of times that other processes are allowed to enter their critical section after a process has made a request to enter its critical section and before the request is granted. So initial attempts to solve problem. So it's using a do while loop. This is the entry section. You have the critical section, you have the exit section, and you have the remainder section. Yes. There is going to be a question on the critical section problem, so giving you guys a heads up. Processes may share some common variables to synchronize their actions. Then we also have semaphores. Yes, we have counting semaphores, and we have binary semaphores too. So semaphores is what? An integer variable, and it comes in two types. You have the binary, can take only binary values, which are 0 and 1, or binary digits. And counting semaphores can take a range of values, and it is used to also implement a solution to the critical section problem. So binary semaphores is used to implement mutual exclusion in critical section problem. Counting semaphores is normally used when resources have multiple instances. For example, printers, processors, cores, processor cores. So semaphores can only be accessed via two indivisible operations, wait and signal. So the wait means there is already a process in its critical section, so nobody can enter. Then the signal is sent that the process is no more in its critical section, so the next process can enter its critical section. So we have semaphore mutex. Initially, mutex is equals to 1. That means we have to wait, and we have the signal mutex too. So a mutex is a locking mechanism, yes, used to ensure that only one thread or process can access a critical section at a time. So when a thread locks a mutex, no other thread can access the same resources until the mutex is unlocked. Now, what I'm trying to explain here, I'm not saying that processes cannot execute. We are saying that in the critical section, I am saying that in the critical section, there is shared data, databases, and all kinds of stuff like that that is shared. And we have to make sure that for those shared resources, we are applying these solutions to the critical section problem. All right. So when a thread locks a mutex, no other thread can access the same resources until the mutex is unlocked. So mutexes are used to prevent race conditions where multiple threads modify shared data simultaneously, leading to inconsistent results. Now let's look at serializability. Now, when several concurrent transactions are trying to access the same data, the instructions within these concurrent transactions must be ordered in some way, so there are no problems in accessing the data. So we can choose to have our time and the operation. Okay. So in our time, we make sure that if a process wants to do a read operation, no problem. We can allow another process to do a read operation at the same time. But if a process wants to do a write operation, then that process alone is allowed to do a write operation. That's where we apply the locks. And a read operation can be done after that write operation is done. Okay. So when several concurrent transactions are trying to access the same data item, the instructions within these concurrent transactions must be ordered in some way so as there's no problem in accessing and releasing the shared data item, which should be consistent. So we have exclusive locks and we have shared locks. And as I was telling you, a read-read operation has a shared lock, meaning multiple processes can be doing reading. Now, a write lock, which is an exclusive lock, is associated with just one process. So it's associated with a database object by a transaction. So the transaction locks the object or acquires a lock for it before writing. So when we say writing operations, it could be inserting, modifying, deleting. Those are some of the things. So we have come to the end of process synchronization. And what we the reason why we need process synchronization is to help solve the critical section problem, you know, because you see, if not, in the critical section problem, we have race condition where you have multiple processes accessing sharing shared data at the same time, and that would lead to inconsistent data. But we also want to protect the integrity of this data. So then we have to be able to make these processes synchronize. And how are we going to synchronize these processes? Using progress, use it bounded weight, using semaphores, using a mutex, that is mutual exclusion, and also using serializability. Okay, thank you and have a good day.